Statement is a beam section is subjected to a shear force of 10 kilonewton. Plot a graph showing the variation of shear stress along the depth of the section. Okay? Depth that is along 60 millimeters. Determine also the ratio of maximum shear stress and the mean shear stress. Okay? So this is the given section, and about the key points or the critical points, we have to calculate the shear stress, and finally we have to plot the shear stress distribution diagram. Okay. So let us write down first of all the given points. Okay. So the value of the shear force is given, that is equal to 10 kilonewton, that is equal to 10 into 10 raised to 3 Newton. Okay. The total depth of the given section D is equal to 60 millimeters. Okay. So this is the total depth. Okay. And the total width given is even 60 millimeters. 60. Right. We know that the formula that is applied to calculate the value of the shear stress is equal to SAY upon B into I. Okay, this could be Y or Y bar. So let us start the computation. So first of all, we'll find out the location of the neutral axis. That is Y bar is equal to neutral axis is equal to summation of AY upon summation of E. Or simply it will be, now what we can do is we can consider the outer section as an entire one, and we'll subtract this slot, a rectangular slot with dimensions 30 by 20, 30 millimeters by 20 millimeters. So I'll write out down as A1Y1 minus A2Y2. So A1Y1 is the outer rectangle with dimension 60 by 60 divided by A1 plus A2. Okay. So this will be A1, that is 60 multiplied by 60 into Y1, that is centroidal axis of this square section. So it will be, since the dimensions are same, so it will be about half of the total depth, that is 30 millimeters. Y1 will be equal to 30 minus A2. Its dimensions are 20 by 30. So 20 multiplied by 30, and its centroidal axis will be half of its depth, that is 30 by 2 is 15, divided by 60 into 60 minus 20 into 30. Hence the value of the neutral axis, it comes to be 27 millimeters. Okay. Now we'll calculate the location, sorry, the value of the this one. Oh, yes, fine. Value of y2. Okay, since we are considering it from the bottom, so it won't be 15. So we'll have to add up 30 plus 15. Okay, so 30 plus 15. Okay. So the value comes to be 27 millimeters. So it was a writing mistake. Now the moment of inertia about the neutral axis. Okay. So that is equal to, so again we'll apply the similar principle, that is we'll compute the moment of inertia of the entire section, outer section about the neutral axis. So neutral axis is now at 27 millimeters from the base, and we'll subtract the moment of inertia of this hollow slot from the moment of inertia of this outer section. Okay. So it will be Ixx1 minus Ixx2. Okay. So now if we consider the outer section, okay, the value, okay, of the centroidal axis of this outer section will be at 30 millimeters from the base, whereas the location of neutral axis is 27 millimeters from the base. Since both the axes are parallel to each other, so we'll have to apply the parallel axis theorem. Same will be the case for the second subsection. It is this hollow slot. So it will be BD cube by 12 plus AH square minus, for second section, BD cube by 12 plus AH square. Okay. B for the first section is 60 millimeters. D is also 60 millimeters. So 60 into 60 cube divided by 12 plus 60 into 60 area, that is 60 square, into H. Now we know that the centroidal axis of this outer section is at 30 and the neutral axis is at 27. So H will be equal to 30 minus 27 bracket square. 30 minus 27 bracket square. Okay. Plus the slot with width 20, depth 30 divided by 12 plus area 20 into 30 multiplied by its distance from the neutral axis. So the centroidal axis of this section, okay, we know that it is located at 45 millimeters from the base and the neutral axis is at 27 millimeter. So the distance between these two axes will be 45 minus 27 and its bracket square. 45 minus 27 bracket square divided by, sorry, okay, that's the term only, 45 minus 27 bracket square. Okay. Hence upon simplification this becomes 1.1124 into 10 to power 6 minus 0.2394 into 10 to power 6. Hence the moment of inertia of the entire section about neutral axis is 8.73 into 10 raised to 5 mm raised to 4. 8.73 into 10 raised to 5 mm raised to 4. Okay. Now we'll compute the value of the shear stresses. So I'll redraw the section once again. This is the location of neutral axis, which is at 27 millimeters from the base, neutral axis. Okay. So the critical points about which the shear stress should be evaluated, calculated, will be the junction of the flange over here, or these two sections, with the bottom section, and the shear stress about the neutral axis. Because if we split this section, it is nothing but junction of three subsections, we can call this as. Okay. So shear stress needs to be computed about this section, okay, and about this width, total width, which is equal to 60, and about these two widths, let's say of subsection 2 and 3, that is b equal to 20 plus b equal to 20. So shear stress will be computed about 40, b equal to 40 and b equal to 60. This is with respect to the junction of these three subsections, and then the shear stress about the neutral axis. Shear stress about the extreme fibers, if we name them as A, B, then neutral axis, and C, will be equal to 0. So shear stress about A and shear stress about C will be equal to 0. Okay. Now let us calculate the shear stress about neutral axis first. So neutral axis, S, that is the shear force, which is given to be 10 kilonewtons into area. So about neutral axis, we are calculating the shear stress. So either we can consider the area above the neutral axis or the area below the neutral axis. So it will be easier for us to consider the area below the neutral axis. So its area will be 27 multiplied by 60. 27 multiplied by 60 into y bar. So again it is nothing but the distance of the centroidal axis of the section under consideration from the neutral axis. Okay. So the total depth is 27. So this height will be 13.5 and 13.5. Okay. So the distance between the two axes will be equal to 13.5 millimeters. So multiplied by 13.5 divided by B. That is the width about which we are computing the shear stress. So the total width will be considered, that is equal to 60, and multiplied by the value of the moment of inertia, that is 8.73 into 10 raised to 5 Newton per mm square. Okay. After calculating, the value of the shear stress about neutral axis comes to be 4.175 Newton per mm square. Okay. And now we'll calculate the shear stress about this junction, okay, of these three subsections. That is about B is equal to 40 and about B is equal to 60. Okay. Let us call this as B1. So tau about B1, that is at B is equal to 40 millimeters. Okay. So since we are considering B is equal to 40 millimeters, so we have to consider the area either above the section. So this is the junction of these two subsections. So we can consider the area above the section or below the section. Okay. So again, it will be easier to consider the area above the section. So its dimensions are 20 and depth is 30. So we know that this distance is 30 and this distance, that is width, is 20. Okay. So tau about B1, that is equal to shear force 10 kilonewton multiplied by area. Area is 20 multiplied by 30 into y bar. So y bar is nothing but the distance of the centroidal axis of the section under consideration from the neutral axis. Okay. So this subsection, sorry, this junction is slightly above the neutral axis. Our neutral axis is exactly, can say, at 27 millimeters from the base. Okay. So this is located at 15 millimeters from the top as well as 15 millimeters from the base of this cross section, and the distance between the neutral axis and its base is 3 millimeters. So the distance between the two axes, that is the centroidal axis of section under consideration with respect to neutral axis, will be 15 plus 3 millimeter. Okay, that is 18 millimeters divided by B, that is 40 multiplied by value of I, 8.73 into 10 raised to 5 Newton per mm square. And the value of the shear stress about this width, it comes to be 6.185 Newton per mm square. Tau at B1, that is at 40 millimeters. Please do not forget the value of the width about which we have calculated the shear stress. Okay. Now we can calculate the shear stress about B equal to 60. So by using the same relation, that is tau about B2 at B equal to 60 millimeters, okay, we can find the value of the shear stress. So tau about B2 will be equal to, so even if we consider the total width about this junction, okay, total width about this junction, so the it is, you can say, easier for us to consider the area which is below that particular section, okay? Or even we can consider it above the section, okay? So it depends upon us which area should be considered. So we'll consider the area again above the section because we know the values. So it will be shear force, that is 10 into 10 cube multiplied by the cross section above the section now. So it will be 20 into 30. Okay, so we'll go for 60 into 30 instead. Okay, so it will be again A1 Y1 minus A2 Y2. So we can do it as the area above the section, that is A1 Y1 minus A2 Y2. So A1 Y1 is 60 into 30 into 15 minus A2, that is 30 into 20 into 15, and divided by B is equal to 60 multiplied by moment of inertia, that is 8.73 into 10 raised to 5. Okay, and the value of the shear stress about this layer, okay, that is about width B equal to 60, comes to be 4.123 Newton per mm square. Okay, now we have the values of the shear stress at the critical points. Now we'll plot the shear stress distribution diagram. Okay, so I can do it here itself. This is the location of neutral axis, which is at 27 millimeters from the base. Okay, about A, then about B1, B2, about neutral axis, and about C. So tau about A and tau about C will be equal to 0. Tau about A is equal to 0, tau about C is equal to 0. I'll project B as well as the neutral axis, and with a suitable scale we'll plot the values. So tau B1 was 6.185, that is about width 20 plus 20, that is 40, 6.185. Tau B2 was 4.123. This is tau B2, that is equal to 4.123 about the total width, that is 60 millimeter, and about the neutral axis the value was 4.175. So it was slightly greater than tau B2. This is tau about neutral axis, that is equal to 4.175. Okay. Now we know that the nature of the shear stress diagram, or the variation in shear stress, okay, for a rectangular section is a parabolic curve. So we'll connect the points, that is A and B, by a parabolic path. Okay, since A and B1, B2 they lie on the same, in the same, you can say, plane, so there will be decrease in the shear stress value. And again from B2 to neutral axis, again it will be a parabolic path, and from neutral axis to tau at C, again this will be a parabolic curve. Okay, this is how we plot the shear stress distribution diagram for the given section. Okay, So again, we'll recall the steps. First, location of neutral axis. Then second one, the moment of inertia of the entire section about the neutral axis. And then the value of the shear stress about neutral axis and the value of the shear stress about the junction of the flanges. It is about B1 and B2 for B is equal to 40 and B is equal to 60. And finally, we have plot the shear stress distribution diagram for the given section. Okay.